Hi all, welcome back to operating system course. So in the last class we had seen about the process, its content, PCB, then about threads. Okay, so today we're going to start with process scheduling. So the objective of the multi-programming is to have some process running all the time. Why? Because to maximize the CPU utilization. Then the objective of your time sharing system is to switch the CPU among the all processes that are available so frequently that the users can interact with each other while the processes are still running. So to meet these objectives, we need something called as process scheduler. So the work of the process scheduler is to select the available process. Like if you have n number of processes that are available, so out of those n processes your scheduler has to select the process such that it can be given to the CPU for execution. So for a single processor system there will be never more than one running process. As the name suggests, single processor system means you will have only one process running at a time. So if there are more processes, the rest have to wait until the CPU finishes the first one or it is free. Okay. So first we'll study about scheduling queues. So what do you mean by queues, right? What are the different types of queues we'll study here? So whenever the process that they enter the system or the program enter the system, they will be kept in a pool, right? And that pool we call it as job pool. Hope you remember that. So I had given you an example of market, right? So whenever the process enters the system, those are kept in a queue that we call it as job pool, or this is also called as your job queue. Okay, this is job pool or it is job queue. Okay, fine. So this job pool or queue, it contains all the processes in the system. Okay, now the processes that are available or which are in the main memory and they are ready and waiting for the CPU for their execution. So those processes will be kept in a list called as ready queue. Okay, so we have now talked about two queues. The first one is job queue. That means all the processes in your system they'll be residing in a pool called as job queue. Okay, so this is your job queue. Now another term is this one, ready queue. So this ready queue is nothing but, so all the processes we have already seen, whenever say suppose this process P1 want to execute, that means CPU has to be allocated to that and it has to be executed. So what will happen, from directly from this job pool you cannot execute it. So this process has to be kept in the main memory, right? We had seen this one. So this is your operating system and say suppose this is P1. Now all the processes that are residing in this main memory, okay, and they are ready to be executed or waiting for the execution. So these processes are kept inside a list and that is called as ready queue. Now do not get confused here. Why? Because I am saying from the job pool or the job queue, your process will be kept in the main memory for execution. That is 100% right? So what will happen is in the main memory also you will have a queue. Now that particular queue we call it as ready queue and it contains only the processes that are ready for execution or waiting for the CPU to be executed. Okay, so we had seen what is job queue and what is ready queue. Now so this queue is generally stored as a linked list. Okay, so what is a linked list now? So in data structures you probably might study or you will be studying this linked list. So linked list, it is nothing but a list where it contains some data, basically which is a node. Okay, we call this as a node and which contains some data, and the next one is the pointer to the next node. So this pointer, this is a pointer, okay, this points to the next node in the list. Again that node will have some data as well as again some pointer. So this is a simple linked list. Okay, now here this ready queue will be generally stored as this particular linked list. Okay. For this to understand, we'll take this example. Okay. Fine. So whenever the ready queue header, right, here you can see the queue, ready queue. So this ready queue will have header. Okay, this is the queue header, and here two pointers will be there. One is head, another one is tail. Fine. The head will always point to the first PCB which is present, or which is present in this ready queue. Okay, and the tail, it always points to the last PCB or the process that is present in the same ready queue. Okay, so first we'll discuss this diagram. So you have a ready queue. Ready queue contains all the processes that are in the main memory and which are waiting for the execution. Okay, now this ready queue, it contains a queue header. This queue header, it has two pointers, one is head and the one is tail. Okay, now this head will point to the first PCB in the list and the tail will point to the last PCB in the list. Again, whenever you have multiple PCBs, process control blocks, that means each process will have its own process control blocks, right? So these are the PCBs. Okay, so whenever you have multiple PCBs in the ready queue, how those will be connected is through a linked list. That means this is a PCB. Now this PCB, it has a pointer which connects to the next PCB, and this process goes on till you have the last PCB. Okay. Now apart from this, in this diagram you can also see magnetic tape unit 0, magnetic tape unit 1, disk unit 0, terminal unit 0. Now these are other queues apart from your ready queues. Okay, so when a process is allocated the CPU, it executes for a while and finally it quits, right? It quits means either it will be terminated successfully, or it will be interrupted by some interrupt, or it waits for some IO operation to be completed. Now suppose that the process makes a IO request, in input output request, to a shared device, okay, such as your disk. Since there are many processes in the system, the disk may be busy with some IO request for some of the processes, okay, or some particular process. Now the process, therefore, it has to wait for the disk. So the list of processes waiting for particular IO device, we call them as device queue. Okay, so here you can see these are the device queues. Okay, it is device queue. Okay, so I'll repeat once again. Each ready queue will be having a queue header which contains a head and a tail. These are the pointers. Now the head will always point to the first PCB in the list. Tail will point to the last PCB. Again, whenever you have multiple PCBs, those will be interconnected via the pointers. Okay. And apart from the ready queue, we also have something called as device queue. So these device queues are necessary. Why? Because whenever the process is executing, it might need some of the IO operations to be performed. Okay. So for example, we'll consider, okay, so here you can see magnetic tape unit 0 and unit 1. These do not have any PCBs. That's why it is shown something like this. So whenever any device queue, if it has only one PCB, that means in that time the head and the tail, it will point to the only process which is in the uh, that particular queue. Okay, here in the disk device queue, what has happened is like, so right now say suppose PCB3 is executing, or disk is serving your process 3, and at the same time you need process 6. Okay, say your process 6, it needs some the same disk for execution or some request, IO request. Okay, that time what will happen is this PCB6, that is PCB of process 6, will be attached at the end of this list, at the end of disk queue or device queue. Okay, so whenever the PCB3 finishes its work, then it would be terminated. Head would point to the next process or the next PCB in the list, and once all the processes before this process 6 or PCB6 has completed its work, then only PCB6 or process 6 would be taken and that IO request would be satisfied. Okay. So this we call it as device queue. Now the common representation of the process scheduling is a queuing diagram, and that is here. This is a common representation of your process scheduling. Okay, so here in this diagram, this is queuing diagram. Okay, so in this diagram, these rectangles, these represents queue that are present, such as your ready queue. Then these are your device queues like IO queue. Then uh, yeah, this is for interrupt queue, this is for creating of the child, something like this. These rectangles, these are the device queues. Okay, the circles, okay, these represents the resources that serve that particular queue, and these arrows, these will indicate the flow of processes in the system. Say for example, say your processes are in ready queue, that means they are waiting for the CPU to be allocated. Say some for some process P0, okay, P0, the CPU has been allocated, and say suppose while executing it needs IO to be it needs some IO operation to be performed. At that time, what will happen? It will go and sit in this IO queue. Through whenever it makes IO request, it goes and sits in this IO queue. Whenever that IO has been finished, whenever that IO has been finished, it will again go back to the ready queue, and again it will wait for the CPU to get allocated. So once it gets the CPU again, then it can if suppose there are no such request, then it will be terminated successfully. Same like that, if a process it wants to create a child process, that means to create a sub process, or it has some interrupt, whenever the process is executing, interrupt occurs, or it wants to create a sub process, or if the CPU allocated, the time allocated for that particular process has been expired at that time, so these device queues will come into picture. Okay, so a new process, as I said, it would be put in the ready queue, then it will wait for the CPU to be allocated. Now once the process is allocated to the CPU and it is executing, so one of these several events would be occurring. So that is your first one is it can raise a IO request, then it will be placed in the IO queue. Then it can create fork a child, that means create a sub process. Okay, so your process it can also create a child process, and it can be interrupted via some interrupt call. Okay, or else the time has been expired for a particular process. Now in the first two cases, like in the IO request and this creation of the sub process, what will happen is your process it will eventually switches from waiting state to the ready state. So it would be waiting for the IO or waiting for the child to get creation sub process, or the child to get created and executed, and after that it would go to the ready queue. Now this this process it continues till the cycle terminates. That means whenever a process is executing, it might need IO request, it might need to create a sub child or sub process. So once it is done, again it will go to the ready queue. If nothing, it terminates, or if needs, again it needs for the second time IO and all. So this process it will continue till its cycle terminates or the process terminates, at which time it is removed from all of these queues, and it's a PCB, that process, that particular process PCB. Okay, so and all its resources would be deallocated. So whenever you have to understand here, whenever the entire process for this particular entire execution of this particular process has been completed, it should be terminated, right? And all the resources which should be allocated or used by this particular process, it would be deallocated. Fine, that's it for today. We'll conclude our session. Thank you.